Hi, in this unit, I'm going to go through the details of AlphaZero. This is something I brushed over quickly in the last unit. So the major innovation of AlphaZero over what had been done previously on Monte Carlo tree search and the upper confidence tree algorithm, UCT, and various things. The major innovation with AlphaGo and AlphaZero is the use of deep convolutional networks. So we're going to have a deep CNN that's computing a probability of an action at each state, and is also computing a value function at each state. So here we have a CNN computing a probability of an action at this board state. So it's computing a probability. So an action in Go is placing a stone at a position. So this is just computing a probability over positions in the board that placing a stone at that position is a good move, is the policy's move, stochastic policy. It also takes the position and computes a value for that position. Now the value is trained to predict the outcome of the game. So the value network is going to tend to produce values between 0 and 1, where 0 is you lose and 1 is you win. And in AlphaZero, these networks are either 20 block or 40 block ResNets, either 20 layers or 40 layers of ResNet. And they also they have two architectures. One is you have two parallel networks, or you have one ResNet and with two heads, one head on the final layer produces a value for the position and the other produces the policy scores. But anyway, the fundamental innovation here is the use of convolutional neural networks. And there's a big debate, who gets credit for AlphaZero? Is it the algorithms that were designed prior to AlphaZero, or is it deep learning, which says, well, you simply replace the value functions with convolutional neural networks and suddenly it works through self-play. It's kind of amazing. So what is the top level algorithm? So the top level algorithm, you're playing against yourself. So to play a game, you have to select a move at each position. And then we're gonna play a game, and that game is gonna have a winner. Now to select a move at a position, just like in chess games, you're gonna grow a tree of possible future positions. You're gonna grow a Monte Carlo search tree over the possible future positions in selecting each move in the game. Now that tree growth process, the first thing to observe about that tree is that it's sparse. You're going to grow a sparse tree, meaning that for any node in that tree, only a subset of the children of that node will also be in the tree. We're going to grow the tree by repeating simulations. A simulation is going to be a descent into the tree made by picking a move at each node until the move you pick at a node is introducing a new node in the tree. So it might be a new child of a node that already has children in the tree. But as soon as you introduce a new node into this sparse tree, the simulation ends. And so each simulation is adding a new node to the tree. Simulation starts at the root, goes down the tree until a new node is added. So the process of selecting a move at each node can be viewed as an instance of the upper confidence tree algorithm. We're going to intuitively have an upper confidence value for each move at each node. And we're always selecting the node with the best upper confidence value. So it's an instance of UCT. Okay, each node in this search tree is a data structure. It has these various components. So this node is representing a position in the game, and I can apply the value network to that position. So, so each node has a value. We also can apply the policy network to that position, and the policy network applied to that position gives us a probability for each move. So the node is storing a probability for each move. It's still, there's no children node in the tree for all those moves, but we're just storing a probability. We're storing the policy at that node. There's also a number for each action, for each possible move, we count how many simulations have taken that move from this position. So remember, each simulation descends into the tree. So a simulation can pick the same move at a given node multiple times. So we're counting how many times a simulation took this action from this node. We're also keeping track of an average of the value of each simulation that passed through this state action pair, but we're including as an initial value just the value of the state. So simulations will reach this state and take this action. The first simulation to reach this state, we just take the value to be in this average. And then for each simulation that passes through that state, the value of that simulation is the value network value for the new node that was added. So that new node that's added gets passed back up and averaged into this value at each state on the path down to that node. Okay, so how do we, so I said that when we do a simulation and we descend into this tree, we're using something analogous to the UCT algorithm to select the move at each node that we reach. So what the selection algorithm is going to do is going to take the action that maximizes an upper bound. It's not really, semantically, it's not going to be clear that this is an upper bound, but we're going to maximize this quantity USA, which I'm thinking of as an upper bound. And this USA is equal to the average value for this pair, which is initialized to just the value of S, but is getting average values every time we select an A. So we're taking this average value and we're adding to it some constant times the policy probability of A. So the larger this is, the more we're adding. So that's, and we're maximizing. So the larger the probability is, the more likely we are to select this move when we take an upper confidence bound. When we take the argmax of this, so we're maximizing this, the higher the probability, the higher this value. But then we take this value that we're getting from the policy network at the state S, and we're dividing by 1 plus the number of visits. This is the number of values that are being averaged into this. So as this goes up, this term becomes less significant, and we rely more on just the average of the simulations that have passed through this action. So that's the sense in which this can be viewed as an upper confidence value. This is becoming less significant the more times we visit it. So that penalty, that upper confidence penalty, the difference between the mean and the upper confidence, is decreasing as the number of visits increase. Okay, so that's how we grow the tree. Now, after we've grown the tree, remember that a game is played by selecting moves at each position, and each move selection is based on a tree that's grown from that position. So when we select the move, so we grow a tree, then at the root position, we have to select a move. So we define a stochastic policy for selecting move A at the root position, which is proportional to the number of times we selected A in that simulation process. This is the number of simulations that selected A raised to the power B, where B is a kind of temperature parameter controlling this. This is going to be a softmax operation, basically, because we're getting a probability, and this would be is analogous to a temperature parameter in that softmax operation. Okay, so we have to. So I haven't talked yet about how we train the policy network and the value network. So that's what I want to talk about next. So this is where tree search bootstrapping is coming into play. So what we're going to do is we're going to construct a replay buffer. You remember replay buffers were important in the more classical reinforcement learning algorithms, actor-critic algorithms, Q-learning. So we're going to construct a replay buffer. The replay buffer is going to consist of triples. of a state, a policy at that state, a probability distribution over actions at that state, and a reward. And the reward is just going to be the final outcome of the game, which is -1 or 1. So this is a 2-valued reward. So S is the root position of one of these search trees. It's a position encountered in the play of the game. It's a root position of one of the search trees that were constructed. This is the distribution over actions that was constructed on the previous slide for this state. And this is whether the game was ultimately won or lost. Right, so we're going to play a bunch of games to the end where they're ultimately won or lost. And then this is our objective function. So we're optimizing. We're going to optimize this loss function. This loss function is saying that the value network should be a predictor of the outcome of the game. So the value network is trained to be the expected outcome of the game from position S. The policy network is trained to mimic the policy pi. So what we're doing is we're selecting these triples from the replay buffer. So this triple in the replay buffer has a policy that we can draw from at random, and what we're going to minimize is the cross entropy from the policies that are learned from the search to the policies that are predicted by the policy network. So we're training the policy network to minimize the cross entropy, to minimize its cross entropy from the tree search based policies. So we're training the policy network to mimic the policies that we associate with the root position. So this is tree search bootstrapping. And finally, there's a regularization term that's regularizing the norm of the parameter vector. There's a shrinkage term. It's worth pointing out that there's nothing in this algorithm that's requiring that we're playing an adversarial game. If we have just a straight up sequential decision-making process, just a standard reinforcement learning problem where we're trying to optimize the outcome of sequential decisions, this algorithm immediately applies. We can still grow our trees. The only thing that happens in an adversarial game is that every time you consider a next position, sort of the roles of the two players flip. But if you just keep the role of the player the same algorithm works. So in principle, the AlphaZero algorithm is a general reinforcement learning algorithm. It could be applied to optimizing the BLEU score in machine translation, where you're thinking of selecting words as a sequential decision process. I'm not saying that's a good idea, but I'm just pointing out that AlphaZero is a general reinforcement learning algorithm. It's not tied to adversarial min-max games. Okay, and we'll continue the discussion of AlphaZero in the next unit. Thanks.